Well, it's about time to go ahead and get started. See, we have at least four of you guys in here, so we're going to go ahead and get started. We are jumping into chapter 24, capacitance, dielectrics, and electrical energy storage. So I'm going to start off by sharing my computer screen for you. I would recommend that you have your ebook open so you can at least look at pictures of what capacitors look like, because that's the main focus of today's lecture. So let me go ahead and share my iPad screen with you guys real quick. All right, so I took the time to write a little bit of an introduction. As I said, it's chapter 24, capacitance, dielectrics, electrical energy storage. Capacitance C is defined as the ratio of the stored charge Q to the applied voltage V and is often made of two conducting plates separated by an insulator called a dielectric. So, dielectric is basically the phrase that we use in the electrical engineering field for insulators, or it's one of the phrases we use. The formula, of course, is C equals Q over V. Its unit is the farad, which is short for Faraday, after Michael Faraday, the brilliant natural aristocrat, as Thomas Jefferson would likely have characterized him. That was large. He was the person that was largely responsible for Maxwell's ability to create the Maxwell equations. In fact, it's Maxwell said he was able to just open up Faraday's notebook and read it, and just could basically translate that into math. Even though Faraday was not necessarily that skilled at mathematics. He was a brilliant mind, and he was able to put things in such a precise wording that it was very easy to translate them in most cases directly into equations. So we now use the unit of the farad for capacitance, and obviously that's just short for Faraday, but it's capital F is what we use. The farad, like the coulomb, is a large unit, so picofarads, microfarads, and millifarads are more common. I did show you that basically, based on the dimensions or the units of capacitance, that would be equal to the units of charge divided by the units of voltage. So that's coulomb per volt. And 1 coulomb per volt is called a farad, or 1 farad. In circuits, the symbols for capacitors include basically just two parallel lines with wires coming off of each side, like you see the first one. There's also capacitors that are I call them polar capacitors. Specifically, they're capacitors that you have to put in a very specific orientation, or you'll ruin them. So they, in other words, unlike a resistor where you can normally just put it in the left to the left, the right to the right, or you could flip it around and take what was the right and connect it to the left, and what was the left and connect it to the right. In other words, the polarity or the direction of the current going through the resistor doesn't matter. And that's often the case with just a plain capacitor, but there are capacitors that they've discovered they can make better and smaller if they choose to let them be polarized, and or choose to make them only be connected one particular orientation. And those other two symbols are a couple of the symbols that are used for such capacitors. It's important that you not confuse them with the symbol for the battery. Notice the difference is the battery has two unequal sides. The capacitor is two bars that are exactly the same size, or maybe one of them might be bent, or maybe they're the same size and straight and an arrow through it. But with a battery, it's a long one and then a little short one. The short one indicating the negative or the low voltage side, and the long one indicating the high voltage side. And sometimes they're written with multiple versions, as you can see in the second and third case. In fact, I looked at the wiring diagram for my Ford F-350, which has a big 7.3 liter, actually 7.4 liter diesel engine that runs on 24 volts. And in fact, they had for the battery, they had short line, long line, short line, long line, short line, long line. In fact, they ended up having 12 pairs of those. So I think within the industry, they might actually represent a single pair as 2 volts. But anyways, that's the symbols. Now, I should tell you that basically capacitors in everyday life are used to store energy, and they're like batteries in the sense that they can run things like a battery does, except all of their juice comes out in a very well defined amount of time. Whereas when you connect a battery to a device, it pours out according to the power ratings of the device that you're using. And with a capacitor, they basically come out all at once, and well, I say at once, but in a very small amount of time. In fact, there's going to be a what we call a time constant, and if you have a circuit with a capacitor in it, and then you have another resistance in it, that could just be the existing wire, but it's usually the wire plus a resistor that's in series, say, with the capacitor. If you then calculate R times C, that value, yeah, and you should check this unit wise, comes out to be units of seconds. And it's the number of seconds required for the charge of a capacitor to go up by a factor of E, basically, 2.71828. Or if you're discharging it, it's to go down by a factor of 1 over E. So, you might also see them, as far as capacitors go, you'll see them all over circuits. The chapter opening photo that the textbook has a photograph of a circuit, and if you look at that, there's two blue capacitors that are sort of a medium blue, and then one of them is turned in such a way that you can see the medium blue and what I'm going to call Carolina blue along the side of it. Those are side by side. Those are capacitors. Then you see another that's sort of round behind a red object, and that round one behind the red object is likely a capacitor as well. This red block in the front that looks a little bit like a chiclet, if in case you're familiar with those candies, that actually has a Z224 written on it, and that kind of worries me because I'm not used to that kind of marking. So I originally thought that was probably a capacitor, but looking at the it does say C719, so I do suspect that is a capacitor because they normally put C's on board diagrams to represent capacitors. And of course, to the far right side is yet another medium blue capacitor, and that one seems to say micro down the side or something along those lines. They also put them in flash battery or flashlight flash units for a 35 millimeter camera. So if you've ever heard somebody use a 35 millimeter camera with a flash, you'll hear them take pictures. You're like, plow, 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 each time the flash fires. But then after the plow noise, you'll hear a zwee, like a really high pitched noise that's escalating in frequency and loudness. It seems like loudness, but it's probably just increasing in frequency. And that's the actual capacitor charging up. And the reason, again, that they're using that is you want a butt ton of power across whatever the flash mechanism is in a very small amount of time. A battery can't do that, but a capacitor can. Additionally, a battery has a limit to the number of times you can charge it and then wear it down and then charge it again and wear it down. In fact, some of them have no option of even charging batteries. So most of the batteries you buy are not automatically rechargeable, even though in some sense you can for a good period of time recharge them, but you've got to be very careful that you don't blow something up. But capacitors can pretty much be charged up and then discharged and charged up and discharged millions of times with no problems usually. Okay, occasionally they do fail, of course, but they usually have very easy ways of telling whether they fail. For instance, the three cylindrical shaped ones that I showed you are that's in the opening photograph for the chapter. The top of them, since it's cylindrical, it's shaped like this, but the top of it has more or less the logo for a Mercedes, that line down and then breaks into a V. And when the capacitor fails, usually what happens is it blows up a little bit and that pops that Mercedes symbol into three little slices, and those three little slices stick up. That's how you can tell that the capacitor has been ruined. That being said, there are capacitors like the ones that NASA uses for some things can actually be ruined and still be functional. In other words, they're not working up the speed, but they can still maintain their capacitance for an extended period of time. I remember seeing a YouTube video on a guy that works for NASA. Specifically, he's one of the people that NASA pays to educate the populace about the stuff they did, and he had this wonderful, I think it was 100 or might even been 1,000 farad capacitor, and it was basically just hundreds and hundreds of big expensive capacitors all connected in parallel so that they basically make a huge capacitance. But anyways, that's enough about capacitance. Whenever you're wanting a big surge of electricity, it's better to use a capacitor as opposed to a battery. And I suspect, though I haven't verified this, I suspect that external defibrillators that are used and hanging in walls of various public buildings, I suspect they use a capacitance as well. I also know of some other things that use capacitance. For instance, if you have one of those backup surge protectors that not only is a surge protector, but actually is a power source. So if your power goes out, your computer will not automatically shut off. For starters, it protects from the surge of a lightning strike, but also it generates enough power that you can keep the stuff running at least long enough to save your stuff and shut it down. Those things are made with batteries in addition to capacitors, and then the capacitor is what slowly trickles out the electricity. And then once that capacitor is completely empty, it can run a little while on the batteries in principle, but generally you want it to be mostly run on the capacitors until you're done. All right, with that in mind, I'm going to start off with an example that is what I call one of our paradigms. So it turns out in 242, you're going to have this chapter where we're going to learn to use this paradigm to derive the capacitance of a capacitor. And I'm going to walk you through those steps. I've even numbered them on the first example. And then you're going to have to be able to do this paradigm, as I said, for a parallel plate capacitor, which is what I'm getting ready to do, for coaxial cable, which has a capacitance, and I'm going to do that one as well, and for concentric spherical shells with a air gap in between them, or it could be some other dielectric between the two shells. In all three of those cases, you use the paradigm to derive the capacitance of that capacitor. So let's start off by doing this example one. It says use Gauss's law to compute the electric field due to an infinitely large flat plate with a uniformly distributed charge per unit area, sigma. So notice the wording, notice the symbols I've used, that sort of stuff. Once you have the electric field caused by the plate, calculate the electric field between two parallel oppositely charged plates. Uh, that step one using Gauss's law is the main step of the paradigm. Computing the electric field between them, that's just extra that you have to do for parallel plate capacitors. Step two is use delta V equals the negative integral of E dot dl to compute the voltage difference between the two plates of area A and separation distance D. So I've went ahead and given you all the parameters you need. The charge per unit area on the plate is sigma. And that would, of course, be in units of coulombs per square meter. The surface area of a single plate is A, and the separation between those two parallel plates is a distance D. And I have the parallel, or one of the plates drawn on a XYZ coordinate system. And then down below that, you might not know what it is right now, but you can sort of make out that this is a blue line and this is a blue line. So those are supposed to be looking edge on to a parallel plate capacitor. You can even see the distances D between them. And the y-axis is on the negative plate, and the blue line that's parallel to the y-axis is on the positive plate. And we're gonna use that to derive the actual electric field strength between the plates. So let's start. I'm going to say solution. And what we need for the solution is C equals Q over V. We need delta V is equal to the negative integral of E dot dl. And we need Gauss's law, the closed integral of E dot dA is equal to Q enclosed over epsilon naught. And my hypothesis, because I know how this infinite plate behaves, and you can actually convince yourself of that by, I'm actually looking at some, by imagining three charges parallel and lying right on the y-axis. The middle charge, the one on the right, and the one on the left. The middle charge causes a force directly above it, or an electric field directly above it that points straight up. The one on the right would cause one that points up and to the left, and the one on the left would cause an electric field that points up and to the right. By symmetry, it seems obvious that that right one is going to produce a or a y component that is exactly equal in magnitude but opposite in direction than the y component for the left one. So that tells us we do not expect the electric field to have any y component. If you then considered three charges along the x-axis, a middle, a back one, and a front one, the same thing would the same arguments would allow you to conclude that there's no x component to the electric field either, and therefore my hypothesis that I use for my electric field in Gauss's law is this. Oops. I switched it to blue. So this is our hypothesis, and it basically says that the electric field is equal to positive E of Z K hat for Z greater than zero and negative E of Z K hat for Z less than zero. So that's my hypothesis. And with that hypothesis, now I can see if I have an object that's parallel to the XY plane, then it'll have a fixed Z. And since it has a fixed Z, that means the magnitude on a plane parallel to the actual plane would have a constant electric field all over that plane. Any plane perpendicular to that, of course, would have an electric field that varies all over it, but because there's a dot product in Gauss's law, it's E dot dA, where dA is a differential area vector on a surface that's not parallel to the XY plane, maybe the side of a soup can or something like that. The actual dA vector would point in these directions depending on what part of the soup label you're on, and that is automatically perpendicular to K, and therefore when you take the dot product of those DAs on the side or the soup label part of the Gaussian surface, that's those terms are going to give you zero. So I think you can now guess what my actual Gaussian surface will be, and in fact I'm going to make it right here. It's going to be what we call a Gaussian pillbox, or what I call a Gaussian soup can. And I didn't like the way I drew that, so I'm going to try to do better. So let's say that's my Gaussian surface, and it actually is shaped like a cylindrical soup can, and the top of the soup can is above the plane, the infinite plane, and the bottom of the soup can is below the infinite plane. And because of that, we're going to have a dA for the top is going to be equal to dA K hat, and the dA for the bottom is going to equal negative dA K hat because it points down. And then this little plate right here, this little differential area element, would have a differential area element dA sub SL is equal to dA, and that's times R cylindrical hat. So what I'm talking about is the R that you know from polar coordinates. In three dimensions, we call polar coordinates cylindrical coordinates because the only addition is a z-axis. So that little R that you recognize from polar graphs, that little r, if you draw a line from the origin to any point in space, that r vector will be parallel to that, pointing in the direction away from the origin and to the point, and its length would be 1 unit long. And in fact, the r hat cylindrical is technically written as cosine theta I hat plus sine theta j hat. So you can see it has no k components. Now, with that in mind, I'm going to start off with the left-hand side of Gauss's law, and the left-hand side is the closed integral of E dot dA. Now, this is a three-part surface. I have the top, I have the bottom, and then I have the soup label cylinder around the side. So I'm going to break this up into an integral over the top of E of Z K hat dotted with dA K hat, plus I'm going to have an integral over the bottom of E of Z. Now, in this case, the dA is actually going to be a negative, so this is E of Z K hat dotted with negative dA K hat. And then the last term is going to be plus the integral over the soup label, and that's going to be a plus or minus E of Z, which all up and down the soup label, some parts when it's above the Z axis or when it's above the XY plane, for instance, will have a positive electric field. In other words, one pointing up, and then below it'll have one pointing down. So that's why I put the plus or minus. Not only that, the Z is going to change all over the side, so I can't pull that out in front, but it is E of Z K hat, and then it's going to be dotted with DA R cylindrical hat, which remember has no K component. It's cosine theta I hat plus sine theta J hat. So when you do the actual dot product on that, you're going to actually get zero. On this one, we end up getting E of Z times A plus E of Z times A. Remember, this one was E of Z, negative E of Z K hat. I didn't write that before. I left the negative off, but the negative is there now. Just notice I had to write it in kind of small to fit it in there. But the negative and the negative combine to give you a positive. That's why I have E of Z A plus E of Z A. And then, of course, because of the dot product between K and R, K hat dot R cylindrical hat is in fact equal to zero. And that's again is because the R hat, which points in the X or Y direction, and the K hat points in the vertical direction. So no matter what direction the R hat is pointing, it's always going to be 90 degrees from the K hat. Therefore, the formula, since they're both hat vectors, the formula is the magnitude of one, which is 1, times the magnitude of the other, which is also 1, times the cosine of 90, which is 0. So that's how that one came out to be 0. So basically what I've got is 2E of ZA for the left-hand side. For the right-hand side, that's Q enclosed over epsilon naught. Now, A is the area that I said, and that basically come from me integrating dA over the top of that soup can. Well, I called the area of the top of that soup can A, and I called the area of the bottom of that soup can A as well. And that also indicates that the area where the soup can actually intersects with the infinite plane, that has an area A as well, because that's going to come in handy for us to figure out what the total charge enclosed is. So Q enclosed over epsilon naught can just be sigma, the charge per unit area, times whatever area is enclosed. And as I just argued, the area enclosed is A. So this is going to be sigma A over epsilon naught. Now I can say left-hand side equals right-hand side. When I do that, I get 2E of ZA is equal to sigma A over epsilon naught. You can see that the A's in fact cancel out. And now we can go back to our original hypothesis and say that the electric field is equal to positive sigma over epsilon naught, excuse me, sigma over 2 epsilon naught K hat for Z greater than 0, and it's negative sigma over 2 epsilon naught K hat for Z less than 0. So that's our electric field. That's part of step one. I'm not quite finished with the rest of step one, but you see that the actual electric field is really a constant. It doesn't depend on Z. Now, that's partly because I actually imagine this plane to be infinitely large, and there's no such thing as an infinitely large plane. It's certainly not one charged either. So, what really matters from a mathematical standpoint is as long as you're closer to the surface of the plane of the plate than you are from the ends by a factor of 10 or higher, then you can pretty safely pretend it's infinitely large. So, for instance, if I put the two plates 1 centimeter apart, I would hope that the two plates are at least 10 centimeters tall. well, actually, I'd say 20 centimeters because I want it to be 10 centimeters from the top to the middle, and then 10 centimeters from the bottom to the middle. So, with that in mind, that's the meets the criteria, the bare minimum criteria for the thing being treated as infinitely large. Now, as you can see, I've labeled down below another diagram of the planes, and we're looking from them from the side. So now I'm imagining, for instance, the positive Q that's marked with purple. That's the plate that I just derived the electric field for, and of course, that electric field points away from that plane because that plane is positively charged, and the direction of the electric field is the direction in which a positive test charge would want to move. So what I'm going to do is realize that in the area between the plates, the electric field due to the purple positive charge is to the left, and to the right of it is going to be to the right, and actually over here it's also going to be to the left. Now, if I think about the same thing with regards to the negative plate, now the negative plate has the same magnitude, it's sigma over 2 epsilon naught, but it's going to be negative, and therefore a positive charge wants to come towards it. So between the plates, we get the negative charge plate is going to want to act in that direction. The negative plate on the left of it is going to want to create an electric field pointing to the right, and the one off to the right hand side is exactly the same as the one in the middle. So you can see that the left hand side you're going to get E equals 0, and the right hand side you're going to get E equals 0. So I'm going to write that in right here and say E equals 0, and I'm going to say E equals 0 over here. But in between, I've got sigma over 2 epsilon naught, and then another one that points in the same direction with the same magnitude, sigma over 2 epsilon naught. When you add sigma over 2 epsilon naught and sigma over 2 epsilon naught, you get just plain sigma over epsilon naught, and that's the strength of the electric field between the plates. And then, as I showed outside of the plates, the electric field is roughly 0. All right, now we've completely finished step one. Now we're going to step two, which says use delta V equals the negative integral of E dot dl to calculate the voltage difference between the two plates of area A and separation D. So I'm going to do that now. I've already taken the time. Dang it. I've already taken the time. Where did that thing go? Nope, that's not what I wanted. Yeah. Okay, I've already taken the time to draw the diagram of the parallel plate capacitor. And remember, basically, it's a distance d, and we're sort of thinking about this coordinate system that I have down here in the bottom corner when I go to integrate this. I'm going to integrate from here to here, and generally speaking, the positively charged plate would be higher voltage than the negatively charged plate. So that's why I'm choosing to go from the initial, which I could pretend has a voltage of 0, to the final, which I could pretend is going to have a voltage V, and I'm going to go ahead and derive that. So what I have to do that, this is step 2. I'm using delta V equals the negative integral of E dot dl. Now, between the plates, we just decided that the electric field is sigma over epsilon naught. So I'm going to write sigma over epsilon naught. But now I have the electric field, instead of oriented in the xy plane with z being perpendicular to it, now in this drawing I've got x being perpendicular to it. So I'm actually moving from x equals 0 to x equals d. Okay, so with that in mind, the direction of the electric field would be in the I hat direction, and then the differential area element. Remember, this integral is technically what we call a path or a line integral, and to commit that, you actually have to evaluate the integrand along the actual path that you're choosing, and you have to indicate which direction you're integrating. When you indicate that, you either have to indicate it by pointing DL in the direction of integration and then making the range of integration from small coordinate to large. Or you can use the limits of integration to indicate the direction, and you just go from the first spot to the last spot in an integral, but then the DL has to point in the positive coordinate direction. So that's the way we're doing that. I'm going to choose to use the DL to point in the direction that we're going, and that direction is in the positive X direction, as you saw at the bottom of the previous page. So I'm going to say this is positive DX I hat is my DL. And since I've now indicated the direction with that, then I just need to go in the direction of increasing X. And the direction of increasing X is from X equals 0 to X equals D. So when you do this, as I told you before, the dot product is what we call a linear operator. The sigma over epsilon naught is a constant. So now I can write negative sigma over epsilon naught times the integral of dx from 0 to d times I hat dot I hat. And of course, I hat dot I hat is just 1. So ultimately, all I get is negative sigma over epsilon naught, and I did go from 0 to D. I actually intended this to come out negative, but I intended this to come out positive, but somehow it looks like I'm coming out negative, so we'll just have to deal with it. Let me double check my electric field. Yeah, my electric field, oh, that's why. My electric field was supposed to point in the negative direction. So I can correct that right now by putting a negative, and I'm going to write it in red so it'll stand out to you guys, but that's it right there. Now that negative with this other negative is now going to make this into a positive, and that's going to make this into a positive. And then, of course, the integral is sigma over epsilon naught times x, and then x evaluated at d minus x evaluated at 0. So that just gives us positive sigma epsilon naught times d, and I should write that in red. So that means delta V is actually equal to sigma over epsilon naught times D, but you could also write that as E times D, because then it would look like exactly the result we found in chapter 21, where we were using the case where the electric field was a constant, and then the voltage difference when the electric field's a constant is just the magnitude of the electric field times the difference distance between them. So I now have step 2 done. I know that the voltage is ED. Step 3 is to use C equals Q over D to derive the actual formula for the capacitance. So I'm going to do that now. 3 gives us C is equal to Q over V. Well, we just calculated the V. It's going to be E times D, or sigma over epsilon naught times D. But additionally, the Q, which is the total charge that's on the capacitor, is really going to be, since we said the area is A of the plates is A, and the charge per unit area is sigma, that means the Q should actually be sigma times A, and the V, of course, is going to be sigma over epsilon naught times D. Now we can see that the sigma cancels out, and this is something that you should always expect when you're actually deriving a formula for capacitance. It should never have any terms related to the charge density of any sort. It should be, strictly speaking, a geometric quantity. So with that in mind, you can now see that the epsilon 0 comes up top, and the answer is going to be epsilon 0 times A over D. And that means the capacitance of a parallel plate capacitor is epsilon 0 over D. And that's the derivation that you are supposed to be able to do. Anybody have any questions on that one? Okay. Well, we've done that now. We did a derivation of basically the parallel plate capacitance, or capacitance for a parallel plate capacitor. Now I'm going to go ahead and derive it for another type of capacitance. I'm going to derive it for I think the next one is coaxial cable. So now I'm going to do this. Let's say use, dang it, I'm going to call this example. use the paradigm to compute the capacitance per unit length for a coaxial cable. So the coaxial cable is basically the wire that comes if you happen to have TV at home. It's the type of wire that you run from your satellite dish, whether you have Dish Network or DirecTV, or from your cable company directly where they have a satellite dish somewhere in the world that they're using. So it's that kind of cable. It's big and black, and if you look at the end of it, you'll see that it has, for starters, a silver barrel or sometimes a gold barrel that marks the end. And then if you look in that barrel, you'll see basically a thin layer of shiny metal. That's actually, if you cut back the housing, you'd see it was actually braided, more or less something that looks like a stainless steel screen or aluminum screen, but it's in a cylindrical shape like this. And then inside of that is some white dielectric material. And then at the center of that is a copper wire. And that copper wire is one of the terminals, and the aluminum screen around the outside is the other terminal. So if you're looking at example 24.2, that's a good indicator of what we mean. Let me draw it really quickly. Basically, what you have is coaxial cylinders. And in fact, the way we look at it is if both of them have some finite thickness, this goes on in principle forever. So we're actually imagining this is an infinitely long coaxial cable. The inner radius, which I'll say is from here to here, I'm going to call that little r. Actually, I'll call that r. I'm going to say r sub a. And the big radius to the inside is going to be r sub b. Okay. And I'm going to go on the assumption that the total charge in the middle for a length L would be Q. Okay. So to do that, I want to look at just the ends and make some sense out of it. But what I'm going to do is draw a coordinate system again. And this time I'm going to draw the coordinate system like this. Actually, I was wanting to use nice straight lines, but it took off of that automatic nice draw setup. So now I'm looking at this. What we're imagining is that there is a inner disk of radius RA, and then that of course goes straight down like this. And then there's another side over here, of course. And like I said, this goes to infinity that way, and this goes to infinity that way. And as I said, this is the radius RB, excuse me, RA. And now, in addition to that, I have the other cylinder, which again was supposed to be drawn neatly, but stupid program won't keep it set up like that. Okay, that looks pretty good. And in fact, I should do another one like that. Okay, now what's going on is this particular inner surface is going to be drawn dashed like that, and then the outer surface, of course, is going to be solid. Again, that was supposed to be a straight line. Don't know why it didn't. And then this is a straight line again. Okay, so we've got that. And I'll remind you that this distance, actually, I have to erase it now because it keeps pooping the bed. So this distance is RA. and this distance is RB, where RB is bigger than RA, and I'm going to say the a length of it L actually has a charge Q. So lambda is equal to Q over L. Now, I know from our derivation of the electric field due to an infinitely long wire, I know that the electric field should only depend on the radial r vector, not the radial r vector in the z direction that has a component in the z direction, but the cylindrical coordinate r vector. So my hypothesis is the following. Again, we need our same equation. So the closed integral E dot dA is equal to Q enclosed over epsilon naught. We need delta V equals negative integral E dot dL, like that. And we need C is equal to Q over V. And we're going to say, as I wrote before, lambda is equal to Q over L. And my hypothesis is E is equal to sum E of R cylindrical times R cylindrical hat. Okay, so my Gaussian surface that I'm going to use is going to be a basically another soup can. So I'm going to draw an ellipse, or yeah, it's more or less an ellipse to represent a circle in 3 dimensions. Of course, the thing keeps turning off like that. Okay, now I'm going to draw a vertical line down this way and another vertical line down this way, and then I'm going to draw another cylinder. That wasn't quite the way I wanted it, but I think I can fix it. Okay, so that's our Gaussian surface. Notice it's at a distance r that is smaller than RB but bigger than RA. So I'm going to say this distance is just plain r. And it keeps wanting to try to draw that better, and all of a sudden it has the ability to maintain the nice drawing. Now, in addition to that, I'm also going to say that this length right here is L. Okay, remember the thing is actually infinitely long, but I'm cutting out a segment L because that segment L will have a total charge Q given by, of course, lambda times L. So now I can do the left-hand side. Left-hand side of Gauss's law is going to be the closed integral E dot dA. But the important thing to remember in this case is it's got to be over a closed surface. So I'm going to have, again, 3 integrals. It's going to be an integral over the top. Notice we're using the same shape I did on the infinite plane. We're using the cylinder, the soup can, if you will. But this time, the top and bottom, which mattered, had all the parts that mattered in the previous problem. The top and bottom aren't going to matter at all here. They're going to give us 0, but the soup label is going to give us what we want. So I can take the integral over the top of E of RC hat dotted with dA K hat. That's the part over the top, plus the integral over the bottom of, in this case, it's going to be E of RC hat dotted with negative dA K hat, and then plus the integral over the soup label of E of RC. Again, that's a cylindrical coordinate, RC hat dotted with dA R cylindrical hat. Okay. Now, we're doing a surface integral here, so technically I have to evaluate that integran on the surface of the green Gaussian surface. But you can already tell, since I can do the linearity trick for dot products, you can tell that you're going to have a R hat dotted with a K hat, and then that equals 0. And the same thing here, you're going to have a R cylindrical hat dotted with K hat, and that too is going to give you 0. So really all you get from the left-hand side is in fact E of R. I'll just leave it E of R. I've done enough to tell you that's the R associated with cylindrical coordinates, so I don't want to write the R sub C anymore. I'm just going to write it as R. But now what happened was the E of R came out in front, the dA came out in front of the dot product, and then I had RC dot RC, and of course RC dot RC is equal to 1 times the cosine of 0 degrees, which of course is just 1. And the integral of dA is the surface area specifically of the soup label. And we know that surface area is 2 pi r times L. So that's our left-hand side. Our right-hand side is Q enclosed over epsilon naught. And of course, the charge per unit length is lambda. So I'm going to call Q enclosed lambda times L. Oops, I used a sort of capital L, so I shouldn't have written that as a cursive L. Let me put it right. And then the Q enclosed is just going to be lambda L. And then I'm dividing that by epsilon naught. So now I can set left-hand side equal to right-hand side. With that, I get E of R times 2 pi R L is equal to lambda L over epsilon naught. I'm sorry, my my L turned out so badly. I'm going to rewrite it. But now you can see that that L cancels out with this L, and you'll see, based on our hypothesis, that we now have the electric field, which I'm going to write in a different color just to stand out. The electric field, E, is actually equal to lambda over 2 pi epsilon naught R, and all of that points in the cylindrical R hat direction. Okay, so I'll put the C back on for the R hat, but not for anything else. So now I've got the electric field, and that's the electric field technically for R, well, actually, I should say for RA less than R less than RB. So in other words, for the distance between them is RB. Now I'm going to calculate delta V. This would be step 2. So right here was step 1. Now I'm going to do step 2. Delta V equals the negative integral. Now, in this case, the integral points the electric field points radially outward. So I'm going to say lambda over 2 pi epsilon naught R cylindrical hat dotted with. Now I'm going to integrate from RA to RB, and what I'm going to go on the assumption is that well, no, let's go ahead and do it like your book. I'm going to go from RB to RA. So I'm going to indicate that with my limits of integration. I'm just going to point the DL in the positive coordinate direction. So in this case, the DL becomes dr times R cylindrical hat. Okay. Using the linearity of the dot product, this can reduce to negative lambda over 2 pi epsilon naught times the integral of r to the negative 1 dr times r cylindrical hat dotted with r cylindrical hat, and of course that's just 1. And of course the integral of r to the negative 1 is the natural log. So I did that, but I also have to say from RA to RB. And that would make, oh, actually, I just have to go from small to large. And no, and I didn't choose to use the DL to indicate the direction. I just said that was a positive. So I'm actually wanting to go to the inner part, which is RA, and I'm coming from the outer part, which is RB. And that's because I'm picturing the outer shell to be negatively charged, and that's why I'm drawing these negatives on here now. So the inside of that surface is actually negatively charged, whereas the outside of the inner surface is positively charged. So that's why I'm integrating that way. With that in mind, I am going to go from RB, which is actually bigger, and I should put that back in purple. So this is RB to RA. And as I said, the integral of r to the negative 1 is the natural log. So now I get negative lambda over 2 pi epsilon naught times the natural log, but you're going to do the natural log at RA minus the natural log at RB. And of course, when you subtract natural logs, that's the same thing as dividing the argument of the log. So this is going to become ln of RA over RB. And that's just because the direction we went. Now remember, the RA is smaller than RB, so if we take the natural log of that, that's the natural log of something smaller than 1, so it's going to come out to be negative, and I can reverse that order and get rid of the negative at the same time by just calling this lambda over 2 pi epsilon naught times the natural log of RB over RA. So now I've got the actual voltage as lambda over 2 pi epsilon naught ln of RB over RA. So with that in mind, I can now calculate the flux, or excuse me, calculate the capacitance. So here is example 2 continued. We've got delta V is equal to lambda over 2 pi epsilon naught times the natural log of RB over RA, which now makes that, of course, a positive quantity. And we're now able to do step 3. And step 3 of the paradigm says UC equals Q over V. Now, the charge, as I told you, was lambda times L. So that's going to be lambda times L. And then the voltage is lambda over 2 pi epsilon naught times the natural log of RB over RA in parentheses. So finally, I can tell you that the capacitance is actually equal to, notice the lambdas canceled out, it's actually equal to 2 pi epsilon naught times L divided by the natural log of RB over RA. Now, I said specifically I wanted the capacitance per unit length, so all I have to do now is divide both sides by L, and I get C over L, which would be measured, for instance, in farads per meter, is now 2 pi epsilon naught over the natural log of RB divided by RA. And that is the capacitance formula for coaxial cable. And sometimes cables are printed with the actual capacitance on the outside, but as a bare minimum, you can just go to the manufacturer's website for any coaxial cable that you can find at Home Depot or Lowe's or Taylor Do It Center or whatever. You can find out the manufacturer, look at their website, and they'll list not only the ohms, which is the resistance of the coaxial cable, but it'll also give you farads per meter to represent the capacitance of the cable. Anybody have any questions on that? All right, so that's the second version. Remember, there's only three that you have to be able to do with Gauss's law. And the three are an infinite plane, making two parallel plates to make a capacitor. We're also going to do a infinite coaxial cable, which we just did, and now we're going to do a spherical capacitor. So what I'm going to imagine now is just like before, the inner part is going to be positive and the outer part is going to be negative. So let me start yet another example. I'm not getting a lot of questions, so I want to ask again. Does anybody have any questions? All of this is something you have to be able to do. I'm literally going to give you a problem in a face-to-face test, whether it be the final exam or the next face-to-face test or whatever, where you're going to have to do, step one, use Gauss's law to define the electric field for one of these situations. Step two, use delta V equals the negative integral E dot dl to find the voltage difference between the positive plate and the negative plate, and then step three, use C equals Q over V to calculate the capacitance. So you got to be able to do that. Now I'm going to say use paradigm to calculate the capacitance due to our capacitance of, that'll be easier, of a spherical shell, oops, of radius. I'm going to call this one RA, and charge Q uniformly distributed over outer surface. So it's a uniformly distributed charge over the outside of a spherical surface, and then inside of a negatively charged concentric spherical shell of radius RB greater than RA. Okay, so with all this in mind, I'm going to quickly draw a coordinate system to give you an idea of what we're talking about here. Okay, now I'm going to attempt to draw a sphere. Okay, now I'm going to attempt to draw another outer sphere. So I'm going to go 3 like that. Okay, that worked out pretty good. So, and in fact, there should be another one out here. There you go. So, and this was actually an inner spherical shell, was actually a shell as well. So I should technically put another circle in here like that. And okay, I'm just trying to center that up, but I'm not going to worry about it. So our Gaussian surface is actually going to be a sphere of radius r that's in between RA and RB. Uh, that's not great, but it's okay. So there's our Gaussian sphere. And it's a sphere. Remember, all three of these circles are technically spheres, not circles. And this radius is just plain little r, as you can see from the diagram that I just wrote. So I first got to derive the electric field between the two plates as a result of that inner plate, which I said has a charge of positive Q. So I'm going to put positive charges here and here and here and here, and then I'm going to put negative charges out here as well. So this is a negative charge, a negative charge, a negative charge, negative charge, negative charge, like that. Okay. And of course, this charge is negative Q. And the other charge, which was ones I drew blue, that is positive charge, positive Q. All right, now solution. Again, we need those same things. The closed integral E dot dA equals Q enclosed over epsilon naught. Delta V equals the negative integral E dot dl, and C is equal to Q over V. Now I'm going to take the left-hand side of Gauss's law. The hypothesis is that E is equal to E of R hat. But this time the R hat is spherical coordinates. So it actually has a K component as well. Huh. My mouth is getting dry, so choking a little bit. Now, luckily, this is one surface, so I don't have to do multiple integrals like I did with the cylinder the last two steps. But what I'm going to say is it's E of R. Let me take another sip. I can't talk. Mm. All right, I guess that's close enough. So E of R times R hat, and that's going to be dotted with dA R hat. And again, since I chose a spherically symmetric and concentric sphere for the Gaussian surface, and the electric field strength I hypothesized to only depend on the radial, spherical radial coordinate R, then on the surface of the sphere, the R is a constant, and so is E of R. So E of R can come out in front, and we end up getting E of R times the integral of dA times R hat dot R hat, which of course is 1, and the integral of dA over the surface of a sphere is of course the area of a sphere, which is 4 pi r squared. The right hand side is Q enclosed over epsilon naught, and notice the Q enclosed was actually just plain positive Q. So I'm going to put this as Q over epsilon naught, and now you can see if we write left hand side equals right hand side, when we get that, we have E of R times 4 pi r squared is equal to Q over epsilon naught. That implies E is equal to Q over 4 pi epsilon naught r squared times r hat. So there's our electric field. Now I got to calculate, of course, that was step one, but now I got to calculate for step two the difference in voltage from the outer plate to the inner plate. So now step two, delta V is equal to the negative integral of E dot dl. Now that's going to be negative, and then our E is Q over 4 pi epsilon naught r squared, r hat, dotted with. This time I'm again going to use the DL in the positive coordinate direction, but I'm going to integrate in the direction of the limits of integration. So I'm actually integrating from outside, which would be RB, to inside, which would be RA. So I'm going to make this RB to RA just like I did before, and then I'll have to let the DL point in the positive coordinate direction, which is DR R hat. Now, that gives us, of course, negative Q over 4 pi epsilon naught times the integral of r to the negative 2 dr. And the integral of r to the negative 2 is r to the negative 1 divided by negative 1. So that makes my sign into a positive. So I end up getting q over 4 pi epsilon naught r for the voltage difference. So that's my delta V. Now I can take step 3. C is equal to Q over V. And that's just going to be Q over Q divided by 4 pi epsilon naught R, like that. You can see, in fact, that ooh, sorry, I forgot to uh, I forgot to evaluate my limits of integration. I wrote them on there and then just didn't do it. But I can't do that, so I've got to actually do this. With that in mind, I got Q over R over 4 pi epsilon naught, but in fact, that has to be evaluated from RB to RA. So what we get is delta V is equal to Q over 4 pi epsilon naught times, now we're going to do 1 over RA minus 1 over RB. And remember that RA is smaller, so 1 over RA is actually bigger than 1 over RB, and that means that this quantity does come out to be positive. But it's smart for me to go ahead and get a common denominator, so I'm going to call this Q over 4 pi epsilon naught. And now I'm going to make this RB minus RA, which of course is a positive quantity, divided by RA times RB. So that's our change in voltage, and therefore we now can compute our capacitance. And remember, the capacitance is Q over V, so that's going to be Q over 4 pi epsilon naught. And then when I divide all that, I'm going to get RB minus RA in the denominator, and I'm going to get RB in the numerator, so that now I can realize that the capacitance C is actually supposed to be 4 pi epsilon naught times RA RB divided by RB minus RA. And that's the capacitance. Anybody have any questions on that? All right, you'll see that this very much resembles some of the actual examples, specifically example 24.2, 24.3, and 20, or excuse me, 24, yeah, 2. Actually, it was the first one was one that was just done in the body of the text, so that's not an example. The coaxial cable one was example 24.2, and the spherical one was example 24.3. So you can see your book's own interpretation of it as well. Anybody have any questions on this before I go to the next thing? All right. So one of the things I want to do is go to the example 24.1. So, and what 24.1 does is it tells us capacitor calculations. A, calculate the capacitance of a parallel plate capacitor whose plates are 20 centimeters by 3 centimeters and separated by a 1 millimeter air gap. So A, we want C equals question mark for A equals 20.0 centimeters by 3.0 centimeters. D is equal to 1.0 millimeters. And that's about it. For part B, it says, what is the charge on each plate if a 12-volt battery is connected across the two plates? So if V equals 12 volts, what is Q? And then for part C, they say estimate the area of a plate needed to make a capacitance of 1 farad. So if C equals 1.0 farad, what must A be? So there's our questions. Okay. Now we've already derived an expression for the capacitance of a parallel plate capacitor, which is what we're dealing with. So I'm going to make use of that, and I'm going to give you a little information as well. So the capacitance was C equals Q over V, and for a parallel plate capacitor, that turned out to be epsilon zero A over D. One thing I will tell you that is that basically this is the result for two plates being separated by a vacuum. Okay, that's what it's really designed for. In fact, even if there's air inside there, you're supposed to use a slightly different epsilon, and they'd call that epsilon sub air, and it would be probably like it would differ by maybe plus or minus one or two in the third or fourth decimal place of epsilon zero. But if you do choose to use something in there that's an insulator other than air, since air is so close to the vacuum value, then you actually could get a different quantity. So I just want to point out to you that when you put a dielectric in there, the capacitance can be given by the dielectric constant times epsilon zero A over D. But sometimes we also often will absorb the kappa or the K into the epsilon and call that a new value of just plain epsilon instead of epsilon zero. So it also can be written as epsilon A over D, where epsilon is equal to K times epsilon zero, and the K is what we call the capacitor constant, or the the dielectric constant, not the capacitor constant. So that's just some additional information that will allow you to get started on your homeworks immediately. There's also formulas for capacitance in series and parallel. I'm probably not going to be able to derive those, but I'll give them to you. But let's go ahead and finish this problem first. So first off, they want to know what's the capacitance. So I'm going to say A C is equal to epsilon zero A over D. Now that's going to be 8.85 times 10 to the negative 12th. That's Coulomb squared per Newton meter squared. And then the A is going to be 20 times 10 to the negative 2 meters times 3.0 times 10 to the negative 2 meters. And that's our area. And then we're going to divide that by 1.0 times 10 to the negative 3 meters, like that. And that's epsilon zero A over D. Notice that I end up getting coulombs per Newton meter. And of course, a Newton meter is a joule. So we actually end up getting Coulomb squared per Newton meter, and a Coulomb per joule is an amp. So you could actually work it out and you'd find that it does work out to be farads. But with that in mind, let's go ahead and calculate the capacitance. I'm going to get 8.85 times 10 to the negative 12th times 20 times 10 to the negative 3 times 3 times 10 to the negative, actually that's supposed to be negative 2 for that case. So 8.85 times 10 to the negative 12 times 20 times 10 to the negative 2 times 3 times 10 to the negative 2. And then I'm going to divide all that by 1 times 10 to the negative 3. And when I do that, I get 5.31 times 10 to the negative 11th farads. And of course, 10 to the negative 12th would be pico. So if I divide by 10 to the 1, that would make it 10 to the negative 12. But then I have to multiply by 10 to the 1 power. So that'd make it 53. So I could call this 53.1 picofarads. And that's the capacitance. Okay. Now, if you were using something with a dielectric other than air, then you could look up in the table from the chapter and it'll give you the dielectric constant. And you just multiply this 53.1 picofarads by the dielectric constant, and that'll give you how it changed. Now, for part B, oops, for part B, they want to know if V equals 12 volts, what is Q? So C is equal to Q over V. That means Q is equal to C times V. So I get 5.31 times 10 to the negative 11th farads for the capacitance. Notice I didn't want to use pico there. I could, and the answer would come out in pico coulombs. That would be fine. And I might still do that, but now I just have to multiply that by 12 volts. So I'm taking the 5.31 times 10 to the negative 11th and multiplying it by 12, and that gives me 6.37 times 10 to the negative 10 coulombs. And of course, 10 to the negative 9 would be nano coulombs. So if I multiply the 10 to the negative 10 by 10, that would make it 10 to the negative 9. But then I have to divide the 6.37 by 10. So that would be C is equal to 0.637 nanocoulombs. Or you could call it 637 picocoulombs if you wanted. But any of those results would work. All right, so that's how we get the actual charge. And finally, we want for part C, we want to know what area would be required for this capacitor to actually have a 1 microfarad, or excuse me, a 1 farad capacitance. So C equals epsilon 0 A over D implies A should be C D over epsilon 0. With that in mind, then, yeah, I'm just making sure my math was right. Yeah, that's all good. With that in mind, I'm going to write 1.0 farad times the same distance, which is 1.0 times 10 to the negative third meters. And now I'm going to divide that by 8.85 times 10 to the negative 12th coulomb squared per Newton meter squared. Again, I want to leave that up to you guys to be able to work out those units. So do that at your earliest convenience. I'm going to take 1 times 10 to the negative 3 and divide it by 8.85 times 10 to the negative 12th. And that's going to give me 1.13, that's one extra sig fig, times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the 8th square meters. So you could imagine that's basically 10 kilometers by 10 kilometers is pretty close to what we're looking at there. So that's really, really a huge area that you need for a 1 farad capacitor with a 1 millimeter distance or separation. Now, I just want to tell you guys, when you connect capacitors, I'll derive this next time, but when you connect capacitors in parallel, let's say this is C1 in parallel with C2 in parallel with C3. Well, when you do that, what you discover is that you could replace all of them with an equivalent capacitance, C equivalent in series, that's actually going to be equal to C1 plus C2 plus C3. And of course, if you had more, you would just keep adding them. Additionally, and notice how that's opposite of what we had for the resistors. When resistors are in series, it's R1 plus R2 plus R3 equals the total resistance. But when you're dealing with a capacitor, that's the formula for when it's in parallel. So if I have instead a voltage V, and then there's a capacitance C1, and another capacitance C2, and another capacitance C3, in that case, I could replace that with one capacitor, and the equivalent there for C equivalent in parallel is 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over C3 plus dot dot dot. Now, what that means, and hopefully you already figured this out from the labs we did with Ohm's law, when you put a capacitor in parallel with another capacitor, the net result will be a capacitance that's smaller. When they're actually in series, the net resistance is, or excuse me, the net capacitance is going to be smaller than either capacitance. So that's the nature of that reciprocal formula. The total capacitance of C1 and C2 and C3 in series is less than C2, it's less than C3, and it's less than C1. In parallel though, it's just the sum of the three. So C1 plus C2 plus C3 is that. So now I've given you quite a bit of stuff where you can go ahead and start doing the homeworks based on that by looking at the examples and looking at these formulas I gave you. So you guys are free to go. It's now time, and I'll wait for the last person to leave in case anybody has any questions for me. But you are free to go. Thanks for coming, everyone.
Hello, I have a quick question
Okay.
on the online test
Yes.
3-4 for chapters 21, 22.
hmm
So I was looking at the instructions for it, and it says it's due March 4th, and it
Yeah, for
says
your
it's
class,
due.
it's March 4th. Why did I send the email to
Okay,
y'all? Because I meant to not send one to y'all.
you're good. No, I'm looking at the due date, and it says March 3rd at 11:59
Oh,
p.m.
thank you. That's just wrong. It will be March 4th. Let me fix that real quick. I think I can do that right now. Thanks for pointing that out. That is helpful. I did not mean to do that, and I didn't warn you guys either. But yeah, you do have one that's due tomorrow at 11:59 p.m. And let me change that due date now. Okay, face-to-face test, online test. There it is. Oh, yep, it does say March 3rd. That's not correct. Okay, so March 4th and March 4th. There you go. Thanks for that, Alex.
Yeah, no, cool. Yeah. Thank you so much.
No problem. Anything else you got?
Um, I'm just digesting, I guess, the idea of using Gauss's law for a two-dimensional plate, I guess,
Yes.
where you were using it, or you're using that idea for uh the cable, and how the outside was negative and the
E-
inside was positive.
right.
So I'm just trying to like visualize that
Yeah, just
Gaussian surface.
remember the scenarios. You really only have three symmetries that work with Gauss's law the way we use Gauss's law. There's
Yeah.
infinite planar, and for that, your hypothesis is E is equal to E of Z k hat above the plane, and E equals negative E of Z k hat for below the plane. And the Gaussian surface is going to be the soup can, but only the top and bottom are going to give you results that are non-zero. When
Okay.
you do cylindrical symmetry, the hypothesis is going to be E equals E of R, R hat, where R hat is the cylindrical coordinate R hat that doesn't have a K component. And you still use soup can, but this time the caps, the lid, the top and the bottom of the soup can give you zero, but the soup label gives you a flux. And then finally, the last one is spherical symmetry. And for that one, you assume E is equal to E of R, R hat for spherical coordinates. And you use a spherical Gaussian surface that has the same center as the Gaussian or as the spherical charge. So if you keep those three sort of facts in mind, you should be able to jump right in and start doing Gauss's law because you know the left-hand side is always going to turn out to be either E times A or E times A plus E times A. And sometimes you actually have to use a formula for A. Like I normally just use A when I'm talking about the lid, the top and the bottom of the soup can for an infinite plane. But when you're doing on a cylinder, then you have to use 2 pi r L for the area. And when you're doing a sphere, you have to use 4 pi r squared for the area. But that's always the left-hand side. It's just E times A or 2E times A. That's it.
No, that definitely clears some things up. I'm just reliving my calculus 3. I guess surface intervals.
Yes, like I said, I haven't even shown you all the gory details of it, but if you want to, just do a search for flux or surface integral, either one, in my YouTube channel, and you'll find videos where I actually show you how to brute force compute it in the way we do it as physicists. And the way they do it in calculus and mathematicians, when they do it, they sometimes do it a little differently. They use a lot of parameterization normally in the math field, whereas we just, brute force take vectors and use trig functions and work it out that way.
I forget, but did you say like in the previous lectures it was located in like near week one
Oh, are
or
you talking about the videos?
yes.
Okay, it's in my YouTube channel, and then remember, there's a search at the top. You don't want to use that one because that search all of YouTube. You want to use the one down below my picture and type in there. Either type in flux, Flux, or type in surface integral. Both of those should give you either one of those searches should result in at least one that'll say calculation of electric flux or surface integral or something along those lines.
Cool. I'll definitely have to take a look at that. All
Yep.
right. Well,
Are you actually in Calc 3 now?
no, I took that over
Oh,
the summer.
gotcha. Did you actually get the surface and line integrals? Because nobody ever normally gets to that. I assumed that TCC wasn't doing any better, but if you were lucky enough to at least know it's there, that's kind of cool.
We did, which was awesome, but
Oh,
it
cool.
was the very last week, and we're also studying for the final, so
Gotcha. It was one of
it
those
was
in and
yeah.
out thing that you had the experience but didn't get to do real homework for or anything,
Yeah,
or
I
not
wish
much
we
homework.
had like another 2 weeks to really,
Yeah.
comprehend it, but I
Was
wasn't
that Miss
lucky
Dale?
enough. No, no, it was online because it
Oh,
was
okay.
summer. Um,
Gotcha.
I forget what his name was.
Gotcha. No problem. I know Miss Dale tries to accommodate my students because obviously is a friend of mine, but she does that quite often because she knows that people that take Calc 1, 2, and 3 ultimately most of them end up taking 241 and maybe even 242. So she often tries to go that extra mile to cover that extra material. But anyways, anything else? There's another person here. I don't know who that is, but do you have a question? Whoever else is here other than Alexander?
Oh, this is me as well.
Okay, that's what I
So
was thinking. It had
yeah,
your initials, so I was afraid it was you. That's cool.
yeah.
Good.
No, I'm at TCC, and I don't want to use the microphone on the lab
Gotcha.
computer so everybody else can hear me. So I listen through my phone.
Do you have any other questions, or do you want me to flip back over some of the uh, examples I just worked or anything? Does any of that need help from you? From me?
I think I got it thus far. I have to go to lab, unfortunately. So,
Okay.
well, not unfortunately, but I have to go to lab.
Yeah, I get you. No problem. Well,
Okay,
have a good one, Alex, and you know how to get in touch with me if you need anything.
I got you. All right. Well, have a good night.
All right, you too. Have a good night. Tell the wife I said hello, or the girlfriend I said hello.
I got you. I got
All right,
you. Bye
later,
bye.
man. Stop share. Bye bye.